everyone, I'm Eng Jia. Today I'm going to share about linear regression. What is regression? To start off, we will introduce the problem of regression. This is the task of predicting a real value target while given a data point as. Regression problems are common in practice, arising whenever we want to predict a continuous numerical value. Some examples of regression problems include predicting house price, stock price, length of stay for patients in the hospital, tomorrow temperature, demand forecasting for retail sales, and many more. Note that not every prediction problem is regression problem. In subsequent sessions, we will discuss classification problem when our predictions are discrete category. Basic element of linear regression. Linear regression, which takes of Gauss and Legend, is perhaps the simplest and by far the most popular approach is solving a regression problem. What makes linear regression linear is that we assume that the output truly can be expressed as linear combination of the input features. Coming for a training data, the first thing that we need is training data. Sticking with our running example, you will need some prediction of example for which we know both the actual selling price of each house as well as the corresponding area and age. Our goal is to identify models parameters that minimize the error between the predicted price and the real price. In the terminology of machine learning, the data set is called a training data and training set. A house, often a house and its price. They comprise one sample and its actual selling price is called label. The two factors used to predict the label are called features or covariates. Typically, we will use n to denote the number of samples in our dataset. We will index the sample by I, denoting each input data point as s to the power I equal to square bracket s power I 1 s power I 2 and the corresponding label as y1. Loss function. In model training, you will need to measure the error between the predicted value and the real value of the price. Usually, you will choose the non-negative number as the error. The smaller the value, the smaller the error. A common choice is the square function for given parameter w and v. We can express the error of our prediction on a given sample as follows. The constant 1/2 is just for mathematical convenience, ensuring that after you take the derivative of the loss, the constant coefficient will be 1. The smaller the error, the closer the predicted value, predicted price is actual price. And the two are equal, the error will be 0. Since the training dataset is given to us and thus out of our control, the error is only a function of the model parameter. In machine learning, we call the function that measures the error the loss function. The square error function used here is commonly referred to as square loss. To make things a bit more concrete, consider the example below where we plot a regression problem for a one-dimensional case example, a model where house price depend only on area. As you can see, large difference between estimate y and observation y lead to even a large contribution in terms of the loss due to the quadratic dependence to measure the quality of a models on the entire dataset. We can simply average the loss on the training side. When training the models, we want to find parameters W, B that minimize the average loss across all training samples. Analytic solution. Linear regression happen to be unusually simple optimization problem. Unlike nearly every other models that we will encounter in this book, linear regression can be solved easily with a simple formula yielding a global optimum. To start, we can substitute the bias by appending a column to the design matrix consisting of all 1s. Then our prediction problem is minimized. Because this expression has a quadratic form, it is clearly convex, and so long as the problem is not degenerate, our features are linearly independent, it is strictly convex. Thus, it's just one global critical point on the loss surface corresponding to the global minimum, taking the derivative of the loss with respect to mass BF equal and W, and setting it is equal to 0 gives the analytic solution. While a simple problem like linear regression may admit analytic solution, you should not get used to such good fortunes, or those analytic solutions allow for a nice mathematical analysis. The requirement of an analytic solution confine one of the respective confine one to an restriction of model that would exclude all of deep learning. Gradient descent. Even in case when we cannot solve the model analytically, and even when the loss surface are high dimensional and non-convex, it turned out that we can still make a progress. Moreover, when those are difficult to optimize models are sufficient superior for the task at hand, figuring out how to train them is well worth the trouble. The key trick nearly all the deep learning and that we will repeatedly throughout this book is to reduce the error greatly by iteratively updating the parameter. Instead of moving the parameter in the direction that incrementally lower the loss function, this algorithm called gradient descent, once convince a loss surface, it will eventually converge to a global minimum, and wow, the same can't be said for non-convex surveys. It will at least lead towards and hopefully good local minimum. The most naive application of a gradient descent consists of taking the derivative of the true loss, which is average of the loss computed on every single example in the dataset. In practice, this can be extremely slow. You must pass over the entire dataset before making a single update. Thus, we will often settle disassembling random mini batch of example every time we need a computer that updates a variant called source stochastic gradient descent. In each iteration, you will first randomly and uniformly sample a mini batch consisting of a fixed number of training data examples. We then compute a derived gradient of the average of a mini batch which regard a model parameter. Finally, the product of this result and predetermined step size more than 0 are used to update parameter in direction that lowers the loss. We can express the update mathematically as follows. To summarize the step of the algorithm, following we initialize the value of the model parameter typically at random. We iterate over the data many times, updating the parameters in each by moving the parameter in the direction of the negative gradient as calculated on a random mini batch of data. For contrary losses and the linear function, we can write this out explicitly as follows. Note the mass and the mass BF are better. Here are more elegant vector notation. Make the mesh much more readable than expressing things in terms of coefficient. In the above equation, masker B represents the number of sample batch size in each mini batch. Is referred to as learning rate and take a positive number. It should be emphasized that the value of the batch size and learning rate are set somewhat manually are typically not learned through model training. Therefore, they are referred to hyperparameter. What we usually call tuning hyperparameters refer to the adjustment of this term. In the worst case, this performed through repeated trial and error until the appropriate hyperparameter found. A better approach is to learn this as part of a model training. This is an advanced topic that we do not cover them here for the sake of simplicity. For the model prediction after completing the training process, we record the estimated model parameter denoted in general head symbol denote estimate. Note that the parameter that we learn via gradient descent are not exactly equal to the true minimizers of the loss on the training set. That's because gradient descent converges slowly to a local minimum but does not achieve it actually. Moreover, if the problem has multiple local minimum, we may not necessarily achieve the lowest minimum. Fortunately for deep neural network, finding a parameter that minimizes the loss on training data is seldom a significant problem. The more formidable task is to find parameters that will achieve low loss on data that we not seen before, a challenge called generalization. We return to this topic throughout the book. Given the learned linear regressions model had mass BFW, top S plus has B. We can now estimate the price of any house outside the training data set which area square feet as 1 and house edge area as 2. Here estimation also referred to as model prediction or model interference. Note that calling a step interference is a misnomer but has become a standard jargon in deep learning. In statistic inference means estimating parameter and outcome based on others' data. This misuse of terminology in deep learning can be a source of confusion when talking to statisticians. From linear regression to deep network. So far, we only talk about linear function, while neural network cover a much richer family of model. We can begin thinking of a linear models as a linear neural network by expressing it language of a neural network. To begin, let's start by rewriting things in a layer notation. Commonly, deep learning practitioners represent model visually using neural network diagram. They represent in figures, we represent linear regression with a neural network diagram. The diagram shows the connectivity among the input and output, but does not depict the weight or bias, which are given implicitly. In the above network, input are S1, S2, .3. Sometimes the number of the input are referred to as the features dimension. For linear regression model, we add upon the input and output one value because there is a single computed neuron not in the graph. We can think of a linear models as neural network consisting of a just single neuron. Since all inputs are connected to all output, in this case is just one. This layer can also be regarded as an instance of a fully connected layer, also commonly called a dense layer. For biology, neural networks derive their name from their inspiration of a neutral sign. Although linear regression predates computation neuroscience, many of the models we subsequently discussed truly owe to neural inspiration. To understand the neural inspiration for artificial neural network, it is worthwhile considering the basic structure of a neuron. For the purpose of the analogy is sufficient to consider the dendrite input terminal, the neutral CPUs, and the axon output wires. The axon terminal output terminals which connect to another neutral via synapse. Information as arriving from other neutron or environmental sensors such as the retina. It receives in the derive. In particular, that information is weighted by synaptic weight, determine how to respond to the inputs, activation or inhibition S to power I, W to power I, or the aggregate in the neutral Y is a sum of I, IW and I plus B. And this information is then sent for further processing in the axons Y, typically after the non-linear processing via sigma Y. From there, either reaches its destination muscles or is fed into another neutron via its derived. Thank you.